This conference will now be recorded.
Hello everyone. Last day we ended in this slide, that is naming carboxylic acid on ring, and some more points we will discuss in this slide, and after finishing this there will be problem related to all these that we have discussed, and then preparation methods of carboxylic acids, and if time permits then also the physical properties of carboxylic acid. So in this example which is in the box, here we can see CO2H that is not directly attached to the phenyl ring. It is attached to long carbon chain. So this is actually not the example when carboxylic acids are present directly on the ring. So the rules that will not be applicable for this molecule. This molecule is actually where CO2H group is present directly on the ring, but not the picture which is this one. Fine. So you can understand the difference. That is why I have placed this picture in this slide. Fine. So here CO2H, as it is not directly attached to benzene ring, so that is why one is given to that carbon which is basically the carbonyl carbon. But when it is not, that is, it is directly present in ring, now number one that will be started from this position. That is the carbon with which CO2H group is attached. So this is the difference. Now some examples we will see. Here we have CO2H group directly present on the ring. So numbering will be started from this position. Now we will move towards this direction because we have CC double bond. So one, there is two position, that is actually the position of CC double bond. So that is why 2 cyclohexene, because now it is not cyclohexane derivative, it is cyclohexene derivative. That is why cyclohexene, we have to write the full term cyclohexene, okay, up to Ne, then carboxylic acid. Similarly for the second molecule, now it is not that is plain ring, it is aromatic ring, right? So that is why numbering will be started from here, and after that we will move towards this direction, because if we move so, then see, it is the position of methyl 2, then 3, then 4, and then 5. Okay, but if we are doing the reverse one, I'm talking about this one. Suppose this is 1 fixed, this is 2, then 3, 4, 5, 6. So if you do so, then the position of Br is 3, position of methyl is 6. But if we follow the red marking, it is 2 and 5. So that is why we will accept 2 and 5. That is the red one, not the blue one. So it is 5 bromo, 2 methyl benzoic acid. Now bromo, though its position is 5, but still you have to mention it before methyl because B comes before M alphabetically. So that is why it is 5 bromo, 2 methyl benzoic acid. One more example, CO2H, this carbon with which CO2H group is there, so that is why 1 will be from here, and then 2 towards this direction because chlorine is present. Fine. And in the same position bromine is also there. Now among chloro and bromo, B will come before C, so that is why first you have to write 1 bromo, then 2 chloro, and then cyclopentane carboxylic acid. So cyclopentane, that is the full it is cyclopentane derivative, so that is why we have to write it the full term, and then it is carboxylic acid. Two more examples. Here we have CO2H group with dotted line and H. That means CO2H and H, they are on the same side. But if you consider OH and CO2H, they are on the trans position. So that is why numbering, nomenclature we are starting trans, because position of OH and CO2H, they are not on the same side. 1, 2, 3, 4. So at 4 position there is OH group, so 4 hydroxy, then cyclohexane and carboxylic acid. Second molecule, here at 1 position there is, that is CC double bond is started. So that is by cyclopent 1 in, because we have to mention the number, the position. Fine. You can also write the name like this, as you have seen here, 2 cyclohexene. That means you can write 1 cyclopentane. That is also okay. But if you write in this way, that is also fine. Cyclopent. So here, rather than writing cyclopentene, we have cyclopent, then one, then ENE. And as usual, we have to end it with carboxylic acid. When it is wrong, CO2H group, it is present in normal chain, we end with the suffix oic acid. But now, as it is present in the ring, so that is why the rule is different. Now we will end the nomenclature with the suffix carboxylic acid, not oic acid. That is the difference. Question related to whatever we have discussed. Now this question that you are seeing here, it is based on resonance structure. In the anion, ACO minus. ACO minus means it is formate ion. Formic acid is ACOH, but when it is, I am saying it is formate, that means H is not present. It is carrying negative charge. So this is formate ion, ACOO minus. In the anion ACO minus, the two carbon oxygen bonds are found to be of equal length. So here you can see we have one carbon oxygen single bond and one carbon oxygen double bond. Fine. But in the question it is mentioned carbon oxygen bonds are found to be equal length. And what is the reason behind it? That you have to find from the options. Now, first option is saying that electronic orbits of carbon atoms are hybridized. Now, this is completely wrong. It is not possible. Here, the actual reason is if I draw the resonance structure like this, other resonance structure will be, now this is the single bond with O minus and double bond is here. But if you take average of these two structure, the average structure will be, this we have discussed in the slide where structure of carboxylic acid is discussed. You can check that slide also. So HC, I will write single bond and then I will use dotted line, because if we consider it is one structure, this is two resonance structure. So this is the that is average of these two, because sometimes it will remain in one form, sometimes it will remain in two form. Okay, so when we take the average of it as if it is of equal length, so the length of carbon oxygen, it will be such that it is not exactly single bond, it is not exactly double bond, it is something in between. Fine. The first option not correct. Second option, C double bond O, this bond is weaker than C single bond O, but that cannot be the reason why these two bonds are equal. Next, the anion ACO minus has two resonating structure. Now obviously it's the correct option. And the last option, why it is not correct? It is saying anion is obtained by removal of a proton from the acid molecule. It is fine. Obviously, when we have the formic acid ACOH and after removal of proton, you get the anion. But it has nothing to do with the bond length, right? The statement is fine, but it cannot be the reason for same carbon oxygen bond length. So correct option is 3. This one. Next, nomenclature related problem. Identify the correct IUPAC name of the following compound. So here the compound is given. Numbering will be started from this position because this is the carbon where CO2H group is attached. Now C double bond O, that is present at that is symmetrical structure. So whether you move from this side or this side, it doesn't matter anything because this position is always 4. Now look at the name. Obviously this is not correct. This is also not correct. Okay, this is also not correct. So see, just look at the suffix, you can easily cancel all these options, because when CO2H group is present in the ring, what we have seen in today's class first slide, it ends with carboxylic acid, but in option B it is ending with on when we use, when there is ketone, right? But it is carboxylic acid. Then methanoic acid. So even if there is some error, just you don't have to, even if you ignore that date also, you can easily cancel B, C, D, because it is also ending with oic acid, but this cannot be oic acid. Then the last option also, it is ending with oic acid. Okay, so that is why these are not correct. Only the first option, 4-oxo, because C double bond O, keto group, as it has lesser priority compared to CO2H. So that is why now you have to use prefix for C double bond O, which is oxo. When it is suffix, it is on. When it is prefix, it is oxo. So 4-oxo cyclohexane. Then position we have to mention. Okay, actually even if you don't mention this position, then also it is fine, but in the option it is given in this way, so you can choose this one. So if you write it instead, that is rather than writing like this, if you write 4-oxo cyclohexane carboxylic acid, that is if you do not mention this position, then also it is okay, because you have already mentioned 4, and we know that the carbon number 1, it is always that carbon where CO2H group is present. So that is why even if you do not mention it, it is fine. And if you see other options, there are so many other errors also. It is starting with 4-carboxyl, but it is not 4-carboxyl. That is actually in option B. What is the main error? Here C double bond O is considered as if it is having higher priority, and CO2H group is considered as prefix. So that is why 4-carboxyl, as if this is present at 4 position. Okay, but CO2H group has higher priority compared to C double bond O. Actually, it has a higher priority compared to any other group, right? So from all point of view, this option cannot be correct. Then option C, 4-oxocyclohexyl methanoic acid. Now methanoic acid, it is treating this group as if it is containing 1 carbon. So this is not correct. This is also not correct. So option A is the correct option. Next question, this is also nomenclature related. What is the correct IUPAC name of the compound that is given? CH3CH double bond, then CH, then again CH double bond, CH into H. So when this the molecule will be given in this way, always draw like this. That is CH3. Actually, we write CH3 like this, but it should not be written in this way. It is H3C because the bond is with carbon, not with hydrogen. So CH3, then CH, double bond, CH, single bond, CH, then again double bond CH, then COOH. So this is the structure. If you write in this way, it will help you to understand, that is to numbering the chain. If you write it in expanded form, it is better. So obviously this is carbon number 1, this is 2, 3, 4, 5, 6. So longest chain, it is 6 carbon. So it will be hex. Now position of double bond is 2 and 4. So at 2 and 4 position you have 2 double bonds. So it should be ending with oic acid because of CO2H. Ending with oic acid and position of double bond 2 and 4. So that is why option B, that should be the correct option. Because if you look at the first option, sorry, there will be I. It is simply saying hexene dioic acid. Another way also you can choose that which option is not correct if you are not comfortable in this way, and that is, suppose you do not know the structure, and if you look at this name hexene dioic acid, can you write the structure? No, you will not be able to write because it is not mentioned what is the position of ene. So that is why this name cannot be correct. Then option C, it is saying penta 1,3-dionic acid, but position of double bond is not 1 and 3. Right? If you write this structure, it will be something like this. First of all, it is penta, that means 5 carbon. This is CO2H. 1, 2, 3, 4, 5. 1 and 2 position, 1 and 3 position, there is oic acid. But at 1 position, you cannot place double bond. That is not possible because of valency of carbon. So this is also not correct. It is not making any sense, the structure that we are getting from this name. Di-OI. Then pentene dioic acid. Sorry, I have done some spelling mistake. Pentene oic acid. Okay. Pentene dioic, but here carbon number is 6. So these two you can easily cancel. And among A and B, B is correct because in A there is no mention of the position of double. Okay. Write the correct IUPAC name for this molecule. So the molecule is given. Here we have CO2H and it is not attached to ring. So Numbering will be from this carbon. Now you have to move towards the longest chain. If this is 1 and if you move 2, then if you write 3 and 4, how many carbon you are getting? You are getting 4, right? In that case, this is ethyl group which is presented to. Actually, both sides, if you move, it will actually be same. If you move in other direction, suppose if you move in this direction, then also it is okay, because whatever direction you move, it is always 4 carbon longest chain. And at 2 position you have ethyl substituent. This is ethyl substituent. Okay, so it will start by 2 ethyl. Now 2 ethyl you can get option C and option D. So 2 ethyl butanoic acid or 2 ethyl pentanoic acid. But pentanoic acid cannot be correct because we have total 4 carbons. So 2 ethyl butanoic acid, that should be the correct option. Okay, so that is why option C is correct. And if you follow the other 2 options, 3 ethyl butanoic acid, but the position of ethyl is not 3, and 2 pentanoic acid, and that is not possible because 2 pentanoic acid, there is no mention of ethyl group, but we have ethyl group as prefix. Okay, so option C, 2 ethyl butanoic acid, that is the correct option. So after finishing nomenclature related problem, now we will start synthetic methods of carboxylic acid. That is the methods by application of this method that will create carboxylic acid. The first method is hydrolysis of acid derivatives. Now hydrolysis means reaction obviously with water, and acid derivative, I have mentioned what is acid derivative in first or second slide of this chapter, aldehyde, ketones and carboxylic. There you can see different types of derivatives are possible. Now derivatives, if I write the structure, general structure of carboxylic acid, okay, so if you replace this OH with some other groups, for example NH2, CN, then OET, so you will get different derivatives of carboxylic acid. So if you do hydrolysis with these compounds, you can get carboxylic acid. But remember, as all these derivative molecules, their reactivity is not same. So that is why, though in every cases it is hydrolysis, but still the conditions required that will be required, that can range from mild to severe. So when the acid derivative molecule, it is very reactive. For example, RCOCl is very reactive. Why? Because Cl, it is having some electron withdrawing power, so it will increase the electrophilic character of this carbon. Electrophilic character means where nucleophile can easily attack, and in this case the nucleophile is water. So H2O will attack this carbon. So if this carbon is very electrophilic, that means it is very electron deficient. So then attacked by nucleophile. Nucleophile is electron rich, that will be facile. So that is why RCOCl is very reactive derivative of carboxylic acid. And you don't have to use very severe condition, harsh condition you don't have to use. But suppose you have taken some acid derivative which is not so reactive. For example, RCONH2, that is amide derivative. Now this is, in this case, this carbon is not very electrophilic, and the reason is because of this type of resonance. And after resonance, the double bond character of C double bond O, that is actually reduced. Now the structure is like this. So electrophilic character of carbon is reduced. So that is why this derivative of carboxylic acid, it is not very reactive. So now if you want to do hydrolysis, you have to use some drastic condition. Fine. So the conditions required, that depends on the which derivative you have taken. So here we have different derivatives. Now in the middle point we have RCO2H, and starting material, it can be RCOCl, acyl chloride, then it may be nitrile. Though here you can say it is not directly acid derivative, but still also from this molecule after hydrolysis you can get carboxylic acid. Fine. It is not considered among derivatives because you do not have the RCO group. Amide, it will require harsh condition. Then you can take a star RCOOR prime. You can take even acid salt, that is RCOO minus, and any salt, that is metal salt. That also can be taken. It is simply basically protonation. The Na will be replaced by H. You can also take anhydride. Anhydride means this type of structure. So here, compared to carboxylic acid, as if this OH is replaced by OCOCr and you get anhydride. So all these molecules can be used, but conditions will not be same. That is, different temperature maybe you have to apply depending on which derivative you have taken. So here you can see this reactivity order, and it is also important to know because sometimes instead of, that is, you can get some problem where carboxylic acid directly will not be mentioned, but some derivatives of carboxylic acid will be given. So if you have proper idea about the reactivity of these derivatives, then only you can solve the question. Okay. So as we are moving up, then gradually the reactivity is increased. So maximum reactive is acid chloride because here OH is replaced by Cl and Cl is electron withdrawal. Anhydride also electron withdrawal because of this group. Though here some amount of resonance is possible, but that resonance that you will find in ester and amide, that is actually more, because in this case the lone pair over oxygen, it can take part in resonance, but if you consider lone pair over this middle oxygen in anhydride, it can actually take part in resonance both sides, right? So as it is shared in both sides, so as if you consider any particular C double bond, the resonance is less because it is happening both sides equally. Chances are it will happen both sides equal. So that is why anhydride are comparatively more reactive compared to ester and amide. So after acid chloride it is anhydride, the next one is ester, next is amide, and the last one is carboxylate. Because in carboxylate, rather than lone pair of oxygen, now you have direct negative charge. So now the resonance will be even more, and higher is the resonance, the double bond character of CO will decrease, and as a result the reactivity will also decrease. Another way also you can explain it, and that is also very interesting, which is leaving group that is present here, because when nucleophile will attack at this carbon, this will be the leaving groups, Cl minus, in case of anhydride it is RCO2 minus, in case of ester R prime O minus, in case of amide NH2 minus. Here leaving group is not present. Now see, when we are saying it is very good leaving group, that means it is least basic. So leaving group, when I am saying it is very good, so it means least basic. Because if it is very strong base, obviously it will be very reactive. And if it is very reactive, how it can be good leaving group? Good leaving group means what? It is stable anion. Then only it can be good. It can be easily removed. Fine. But if it is not stable, that means it is very reactive. And if it is very reactive, it will always try to remain attached with this carbon. So that is why, as in case of RCOCl, leaving group is very good because it is stable. Negative charge is stable over Cl because chlorine is electron, that is electronegativity is high. Then as you move down, the leaving group capability, that is decreasing, but basicity is increasing, and we know that NH2 minus base is very strong base, and here negative charge, though it is nitrogen, you can see it is electronegative, but it is not like as you see in case of Cl. And in this case, in case of anhydride also, it is very stable because this type of resonance is possible. Fine. So as we are moving down, basicity is increased, and that is why leaving group capacity, that is how fast it can be removed, that is the leaving group capacity. So leaving group capacity will decrease. So NH2 minus is basically amide ion, anion, is very reactive, very strong base. It is always searching for some acidic product. So it cannot be very good leaving group. It will always try to remain attached with carbon. So this is the reason why reactivity is decreasing as we are moving from acid chloride to anhydride to ester to amide. Second method, oxidation of primary alcohol and aldehydes. Okay, primary alcohol, when I'm saying, that means the OH group, it is obviously attached to one carbon, and that carbon is attached to only one carbon and two hydrogen. So that is the definition of primary alcohol. If you use primary alcohol and also aldehyde, because if you see alcohol first in presence of oxidizing agent, it is not directly converted to acetic acid. First it is converted to acetaldehyde, that is aldehyde, and then it is converted to acetic acid. But if you directly start from aldehyde, then also your product is ultimately same. So both can be used. Oxidizing agents that are normally used, KMnO4 in acidic medium or alkaline medium, potassium dichromate, it is always in acidic medium. KMnO4 can be in both medium, but K2CR2O7 it is always in acidic medium. Okay, here we have taken the example of ethanol or ethyl alcohol and acidic condition H plus K2CR2O7. This sign we use to show oxidation is occurring. First we are getting acetaldehyde. So as it is very strong oxidizing agent, the reaction will not stop at aldehyde. It will directly go to acetic acid. But suppose you are using some mild oxidizing agent, there are some special oxidizing agent which are used to stop the reaction at this position. But here our purpose is not to stop the reaction at aldehyde position. We want ultimate product carboxylic acid. So obviously we have to use some strong oxidizing agents like K2CR2O7, sometimes it may be Na2CR2O7 and potassium permanganate. Another oxidation method which is used for alkyl benzene. Now when I'm saying alkyl benzene, obviously benzene ring will be there, and with this benzene ring there may be any alkyl group. It may be methyl, it may be, in general I am writing R, but R may be methyl, it may be ethyl, it may be some branching, it may be tertiary butyl, it may be isopropyl, but it is always benzene ring attached to some alkyl group. That is why we are saying alkyl benzene. And when you are doing oxidation, you will always get aromatic carboxylic acid. Vigorous oxidation of alkyl benzene with bromic acid or acidic or alkaline potassium permanganate. You can use any of these reagents. The entire side chain, because the side chain it may be one carbon, two carbon, sometimes branching may be there. But interesting point is you will always get CO2H group directly attached to benzene ring. Whatever is the length of side chain, that doesn't matter anything. If it is methyl benzene, you will get benzoic acid. If it is ethyl benzene, then also you will get benzoic acid. Fine. So see, these are the examples. Because this one carbon which is directly attached to benzene ring, that is always oxidized. So even if you take long chain, it doesn't matter anything because it will always break at this point. Rest of the portion it will be converted to some other method, because the condition is very I mean to say the reagent that we are using, that is very strong reagent. Okay, so whatever is the chain size, now see this is another ring is attached, but here this CC bond will be broken, this CC bond will be broken, so you will be remaining only this with these two carbon, so you are getting dicarboxylic acid. And then the next one, that is also very interesting because all these methyl groups will be gone, only the carbon directly attached to benzene ring will be there. Okay, but here reaction is not possible. Why it is not possible? Because the group that is attached, at least one hydrogen must be there. Here you have all methyl groups, there is no hydrogen attached to this carbon, right? So that is why reaction is not possible. You can see in other cases there is hydrogen present always, right? So here reaction not possible. Then we have taken our long chain and with a branching also, but it doesn't matter anything, it will always break at this position. So you are always getting carboxylic acid directly attached to benzene. Okay, so this method is oxidation of alkyl benzene. After third method, this is the fourth method. Now we will use some organometallic reagent. Just know what is organometallic reagent, that you have to know. Organometallic, that means organo, this term we mainly use for carbon, and metallic, that term is there, that means some metal must be there. So it is organometallic compounds whenever you will have, there will be present of carbon metal bond. Now carbon metal bond, we know that metals, they are electropositive, and electronegativity of carbon compared to metal, it is always high. That means if you consider polarity of this carbon metal bond, it will always be negative towards carbon. I am writing del negative, partial negative charge and partial positive charge. Fine. So the side, the carbon side, that will be always acting as nucleophile, and this side is basically positive side. Okay. So organometallic reagents, the first name that comes in our mind is Grignard reagent, obviously. In Grignard reagent, there is carbon magnesium bond. The metal is used magnesium, but it is organometallic compounds are not restricted to Grignard. Obviously, this is the most common. In your syllabus, it is the most common, but there are some other types also. So in Grignard, we have carbon magnesium bond, where the carbon side is negative. Organometallic reagents reacts with carbon dioxide, and first it gives metal salt of carboxylic acid, and when you acidify it, that is upon treatment with acid, ultimately you get carboxylic acid. And here the carbon dioxide that is used, that can be used either in gaseous form. In that case, you have to bubble it through the solution, or you can also use solid dry ice. Now see the example. Grignard reagent, we have taken RMGBr. This may be an alkyl group, it may be pH also. Now this RMGBr, here we have carbon metal bond. Now carbon, that is the negative side, as I have said. So this R you can consider as if it is R negative. Okay, so as if it is nucleophile. Now you are using carbon dioxide, right? So this nucleophile, it can attack the carbon, and one of the C double bond O, that will be now O minus. Now if this is the negative part, obviously the rest of the part, that will be positive part, and now you have negative charge over oxygen. So the structure should be like this. This negative charge, that will be balanced by the positive part of Grignard reagent. Double bond O, this side there is no change. So this is metal salt of carboxylic acid. But finally, if you acidify it, as you can see, H2O plus is mentioned. So this OMGBr will be converted to OH, and the fate of MGBr is now as if it will take OH from water. So if I write water in this way, HOH, so this MGBr, that will be with OH, MgOHBr, and O minus, that will be attached with hydrogen. Okay. Another example, which is not Grignard reagent, but you should also know it. Here we have taken phenyl lithium, PHLi. There is another important molecule also, which is butyl lithium. 4 carbon chain, 1, 2, 3, 4, and then lithium. This is known as N-butyl lithium because it is linear chain. Now phenyl lithium, this is also organometallic reagent because you have carbon metal bond. Carbon metal bond, if you have, then it is treated as organometallic reagent. So here also this pH, as if it will behave as pH minus, though I shouldn't write it in this way because it does not exist in that part in this way. But pH and Li, if you consider polarity, obviously this side is more negative. So now it can attack carbon dioxide, same mechanism as you have seen in the previous example. Finally, you have to acidify it, and you will get here we are getting aromatic acid because we have started from PHL. Okay, so this method where starting material for preparation of carboxylic acid is Grignard reagent, organometallic reagent, though the most common example is Grignard reagent, but in general it is better you say organometallic reagent, because in organometallic reagent we have carbon metal bond. Okay. Number 5 for preparation of carboxylic acid. Now under number 5 we will have some ABC, but in general it is oxidative cleavage of either alkene or alkyne. Okay, that is CC double bond or CC triple bond. So first we'll see what happens in case of CC double bond. So for CC double bond we will do ozonolysis, but remember ozonolysis can be two types. Obviously we will use ozone because it is ozonolysis. First step you are using ozone, but the second step may be two types. It may be oxidative workup, that is you are using some oxidizing agent to get the final product, or it may be reductive workup. You are using some reducing agent to get the final product. So O3 plus oxidative workup, that combination you have to take, not reductive workup. Because here if you normally you will see most of the examples that is given in book, it is mentioned for ozonolysis O3 and zinc or water, but zinc and water when it is mentioned it is actually reductive workup. So in that case you cannot get carboxylic acid. Suppose if you are doing ozonolysis O3 and you are using zinc water, you will end up with product like this. There will be simply CC cleavage. You will get from one side, left hand side, this molecule propanaldehyde, and from the other part you will get CH3CH. Okay, simply bake CC double bond, put some C double bond. But when it is oxidative workup, H2O2, that means oxidizing agent you are using. So now how you will get this type of aldehyde. So this aldehyde now will be oxidized to, see, CH3, CH2, CHO, propanaldehyde, and now you will get propanoic acid. Similarly, this is acetaldehyde, but ultimately as you are using H2O2, it will be CH3COOH. So when it is H2O2, you are using oxidative workup. End product will always be carboxylic acid. Okay. So how we will write the carboxylic acid? It is always better first write the keto compounds that you will get. It may be aldehyde or it may be keto, depending on what type of molecule you have taken. But when it is keto you are getting, for example in the second, basically when you are breaking this bond, you are getting cyclohexanone. But here further oxidation is not possible because oxidation by oxidation when you are getting carboxylic acid, it is only for aldehyde, not for ketone, because for ketone very drastic condition is used, and even if you use that drastic condition, what happens, any of these CCO bond will be broken. That is completely different reaction. Remember, here you cannot get from this part, you cannot get any carboxylic acid under this condition. For to get that is to break this CC bond, you have to use very strong oxidizing agent. So normally we do not consider ketone as a starting material for carboxylic acid. So you will not get carboxylic acid from this part, but from the other part it is aldehyde because you have one H, and that aldehyde can be carboxylic acid. Okay. Then cyclohexene derivative, here we have one hydrogen. Now see, as it is cyclic, that is this side is being present, when you will break it, basically COCH3. Now see, this part there is no change, but from the other part, after COCH3 there are total 1, 2, 3, 4 CH2. So 1, 2, 3, 4. Now from this position, the CHO that you will get, that will be converted to CO2H. Okay, other part it is still ketone. Then for this molecule, this is completely different because now you have terminal CH2. So when you have terminal CH2, from this part you will get ketone. But when it is terminal CH2, basically what we should get? We should get first ACHO, formaldehyde. But under this condition, that is reaction condition, formaldehyde cannot remain in formaldehyde. Sorry, you will not get formaldehyde. Basically, you are using oxidative reaction. So first it will be formaldehyde, then it is formic acid, because it is oxidizing agent you are using. But formic acid under this condition cannot remain in formic acid form. So ultimately CO2 will be removed. Okay, and basically these two hydrogen, this part is as if CO2, and the two hydrogens will be removed in presence of oxidizing agent. These two hydrogen with another oxygen atom, it will make water. So basically here water is also put. So remember, whenever you have formic acid in presence of oxidizing agent, ultimately it will produce CO2 and H2O. But that is overall, if I say, if you have CH2 group, terminal CH2 group in alkene molecule, you are not getting carboxylic acid, because formic acid you cannot get. Ultimately it will be converted to CO. So last example, basically you are not getting any carboxylic acid. Okay. Now what about alkyne? In case of alkyne, actually there is no reductive or oxidative workup. Directly you can use H2O. Here the mechanism for ozonolysis, if we go into the details, though that is not required. But if you are interested, you can find it in a book. You will see that there oxidizing agent not required. Even without that also you can get carboxylic acid. Okay. So under alkyne, this is alkyne where one side we have alkyl group, another side we have hydrogen. So if you take this type of alkyne where terminal CH bond is present, KMnO4 KOH, H2O plus, then what we are getting? We are getting RCOOH and CO2. Okay. Sorry, I shouldn't write it here because two different reagent combinations are shown. So better just neglect this part. This O3 and H2, that is used only here. Actually, whether you use O3 or H2O or this reagent combination, that is alkaline medium KMnO4 and H2O plus, then also you are getting actually the same type of reaction. So you can use any of this reagent, either O3 or H2O or KMnO4 in presence of alkaline condition, and ultimately you have to acidify it. So RCO2H, when you have R group on one side, other side where you have carbon hydrogen, you will end up with CO2. Now we have taken alkyne where both sides you have same group. Now same carboxylic acid you will get two times. But if these groups are different, R one side, R prime another side, now you will get two different carboxylic acid. Okay, so this is these are the acid how we will get from alkyne, that is mentioned. So any of this reagent, either use ozone, that is ozonolysis in presence of water, no oxidizing or reducing agent, or you use KMnO4 alkaline condition, and finally acidification. Another method we will see, oxidative cleavage with hot KMnO4, because normally if you use CC double bond and if you use cold dilute KMnO4, what type of product we get? We get CC, from CC double bond, we get dihydroxylation like this. But there is no cleavage. But if you use hot KMnO4, now there will be cleavage, whether it is CC double bond or CC triple bond. Now CC triple bond you have already seen in the previous example. Here we will also see the same reaction again, just to understand that here the KMnO4 that you are using, it is actually hot KMnO, okay, not dilute. Then only this type of cleavage is possible, because ultimately CC bond is broken, right? So here simply cold dilute solution will not be enough. It must be under hot condition. Another example also. Actually, these two examples you have already seen in the previous slide, right? I mean these two. But if you use O3 and H2O, then also you will get same product. So that is why they are also mentioned here as well as in this slide. Now this example is new, and here if this CC bond is broken in presence of hot alkaline KMnO4, so from this part you are getting this acid, and this part is simply 3 carbon chain, so this is propanic acid. What about alkene? CC double bond. So when it is CC double bond, you are using same condition. Then from this part, when you have 2 alkyl group, you will end up with ketone. Okay, but the other part where you have 1 hydrogen, 1 R group, now you will get the salt form of carboxylic acid because the condition is basic. This is also actually carboxylic acid. You just have to acidify it, then you will get the corresponding carboxylic acid. But as the medium is basic medium, so carboxylic acid cannot remain in carboxylic acid form. It will always be in some salt form. So if it is KOH, it will be potassium salt. So that is why carboxylic. Next, if you take this type of alkene where this side is actually same as the first example, but the other side, now you have 2 hydrogen attached. So in this case also, basically you will get formic acid, but as I have said, in this condition, formic acid will not remain in formic acid, it will produce carbon dioxide. So basically, in this case, you are not getting any carboxylic acid. Okay. So this is actually not synthesis of carboxylic acid, but you should also know it that when you have terminal CH2 or both sides, there are 2 R groups. In both sides, you are not getting any carboxylic acid. There must be 1 R group, 1 hydrogen. Now in the third example, see, in this side, you have basically 2 R group. This is also 1 R group, this is also 1 R group. So what you are getting? You are getting ketone. But the other side, you have 1 hydrogen and this CH2. So that is why you are getting CO2H. If I number this carbon, it will be easier for you to understand. This is 1, 2, 3, 4, 5, 6. This is 1 because methyl group we have not numbered. 6 carbon is basically converted to COOH. Fine. But remember, 1 hydrogen must be there. Question related to preparation methods. RCH2CH2OH. So this is alcohol basically. R group, it may be any. We do not know what is this group. It can be converted to RCH2CH2OCOH. Now see here, except this R group, in between R and OH, you have 2 carbon. But the product that you are trying to make, you have, considering this C, it is 3 carbon. That means you have to enhance the number of carbon. Now what reagent you will use? The correct sequence of reagents is, sequence of reagent means 1 by 1 you can use. In the first option, it is mentioned KCN. Now when you are using KCN, basically this OH, at a first glance it seems it will be converted to CN, as if nucleophilic substitution, OH is replaced by CN, right? And then once you get RCH2CH2CN, and if you are doing hydrolysis, now when I'm saying hydrolysis, it must be acid, and sometimes it is mentioned also as H2O plus, both are fine. So remember the first method that we have discussed, when you take a derivative of acid, in that slide also, those cyano compounds are not directly considered as derivative, but cyano, that is C triple bond N, as if it is analog of COOH, because ultimately it is C triple bond N. Okay. Here also OH2O, that is you are doing hydrolysis. So water will attack at this carbon. So from RCN also we can prepare carboxylic acid, that is already mentioned in that slide. So now what you will get? You will get this one. And the second option, try to understand the difference. Second option, first PBr is used. Then actually PBr, this type of compound does not exist. If it is PBr3, it is fine. Then KCN, then H2. But how we can use H2? We have to do hydrolysis. We have to use some acidic condition. Okay. Then third option, now we have PBr3. Now this is actually the compound phosphorus tribromide. Then KCNH plus, And in the last option, now ACN is used first. Here KCN, that is the salt, is not taken. Hydrocyanic acid is taken. Rest of the part there is no change. But see, this is not at all possible, because whether you take ACN or KCN, after using PBr3, what will happen? If Br will be there, and hydrolysis of Br is not possible. So it must be Br, that is a bromine containing reagent first, then cyan. It should be like this. Now this option is correct, because first option, here OH cannot be replaced by, that is in presence of Cn minus, it cannot be replaced directly. So that is why first you have to use PBr3. So once you use PBr3, RCH2CH2OH, it will be converted to RCH2CH2Br. Next, when you are using KCN, that means Cn minus source, that will attack here and Br will be removed. So from CBr you can make CCN, but not directly from OH. That is why third option will be cut, not the first one. Direct replacement of OH by Cn is not possible. Okay. Here we have cyclic anhydride. Remember what is anhydride? Anhydride is RCOO, then COR. Now these two are maybe same or different. But if I join these two terminal position, now we will get cyclic anhydride. So look at this portion. This is actually cyclic anhydride, and it is asking the total number of carboxylic acid group that is possible in this product. So what we are using here? We are using first H3O plus and heat. And what we know, that when we have anhydride, you are using hydrolysis condition, that is H plus and H2O, or you can write H3O plus. What you will get? You will get carboxylic acid, COH2 molecules you will get if these two are groups are same, right? That means this cyclic anhydride also, it will be broken. From this part you will get one carboxylic acid, from another part you will get another carboxylic acid. So from right hand side part of the molecule, we should get two carboxylic acid attached to this ring. But this is not end of the reagent. We are also using O3H2O2. That means we are doing ozonolysis under with oxidative workup. Remember oxidative workup we have discussed, H2O2. That means now look at the left hand side part of the, you have CC double bond, alkene. So that must be broken. Now if it is under, that is ozonolysis in presence of zinc H2O, you get two aldehyde because we have two hydrogen. But as we are using oxidizing agent, so after cleavage of CC double bond, there will be two CO2H. This is the complete reaction. First, when you are using H2O plus number one reagent, you are getting two CO2H. This ring is broken, right? Now, when we are heating it, as there is heat also, here this is very interesting. If you just stop at H2O plus, it will be converted to CO2H. But as we are also heating, now when we are heating CO2H, if it is present, that is in this position. Now what I am trying to say, it is actually beta keto acid. Beta keto acid means I am just enhancing this part, CO, then there is actually another bond, but suppose if I write in this way, then COOH. Okay. Now with respect to CO2H group, this is alpha position, this is beta position. So at beta position you have keto group. So that is why I am calling it beta keto acid. And beta keto acids, when you heat it, there is always removal of CO2. And how it occurs, I am going to show it. So if I write the molecule, only the beta keto part I am considering, CO. So CO2H group I am writing in this way. There is a special reason for that. So now this type of mechanism will occur. This CC bond will be broken. So what you will, there may be any group or not, that is not important. But ultimately what you will get enol type of structure. C double bond C. Okay. There may be 2 hydrogen or maybe 1 hydrogen, 1 any other group. So this part is basically removed as carbon dioxide and you are getting some enol. But it will not remain in the enol form. Ultimately, it will also be converted to keto form like this. So that is why if you do all these processes, ultimately these 2 CO2H, this portion will be removed as 2 carbon dioxide. So 2 CO2 is mentioned, and here when this CO2H group is complete, as if 2 hydrogens will be remaining. So be very careful about the reagent. If it is only H2O plus, the number of CO2H group will be high, it will remain. But as heat is also there, so there will be decarboxylation. So from right hand side part there is actually you are not getting CO2H, but after ozonolysis oxidative workup, this CC bond will be broken. So this carbon will be converted to CO2H, another carbon that will also be converted to CO2H. Okay. So ultimately total number of carboxylic acid groups in the product P, it is 2. So this is integer type of question. Fine. And the same question, if this heat sign is not there, now it will be 4. Answer will be 4 because decarboxylation will not take place. Okay. Acetic acid is obtained when different methods are there. Methyl alcohol oxidized with potassium permanganate. Methyl alcohol is CH3OH. There is only 1 hydrogen. Okay. If you do oxidation with potassium permanganate, you will get formic acid. But we want acetic acid. And acetic acid is, there are total 2 carbon. So how we can get, that is, we cannot use methyl alcohol as the starting material, right? Then calcium acetate distilled in presence of calcium formate. So you have taken calcium salt of acetic acid, calcium salt of formic acid. And remember, when we have discussed preparation methods of ketones, there we have discussed this method. We take calcium salt of different carboxylic acid, and if you distill it, you get some ketone compound. So this is preparation method for ketone, not acetic acid. And the third option, acetaldehyde is oxidized with potassium dichromate, and that is K2Cr2O7 and sulfuric acid. So this can be correct. And the last option, glycerol is heated with sulfuric acid. So see, these 2 are actually number 2 option. This is number 4. These 2 are not correct. So calcium acetate, calcium formate, they are calcium salt. If you heat it, basically you will get 2 acetaldehyde molecule. You can also check the preparation methods for ketone compounds. There you will find the same reaction. And this is glycerol. When you are heating it, concentrated H2SO4, basically what will happen, one part, that is one terminal position CH2H, that will be converted to as if it is CHO, but from this part there will be CC double bond formation. So this is acrolein. Fine. And this scheme that you are seeing here, that is also discussed in chemical properties of alcohols. So you can also check that. So this is option 4, which is not possible. Only option 3, acetaldehyde, you are using potassium dichromate, K2Cr2O7, acidic condition, you can get acetic acid. So we are at the end of the session. Some more problems and physical properties, chemical properties of carboxylic acid will discuss in the next class. Thank you for listening. We are ending the session here.